All right, guys. So what we want to look at, just to kind of lead into what we're talking about today, is we want to look at an exponential function here. So here's an example, real quick example. A $1,000 investment is compounded by 2% annually. So we want to go through, first we want to write a function that represents the amount of money over time. So if you don't see it right off the bat, you can look at a couple of examples here. We can look at year one. And what happens in year one. So in year one, we take a $1,000 investment, and compounded by 2% annually means you earn 2% interest every year. So we want to multiply that by 1.02, and that's going to increase that by 2%. So that gives us $1,020 for that one. In year two, that means that 2% interest is going to be applied twice. So we're going to take our original amount, 1,000, and apply 2% to it twice. So 1.02, and then multiply it by 1.02 again. So now we've compounded that interest on year two, and that gives us $1,040.40. Year three, we're going to apply that same process, and hopefully just looking at a couple examples of this, you can kind of identify the pattern. This is 1.02, 1.02 times 1.02 times 1.02, and that's going to give us, if we round here, that'll give us $1,061.21. So the important part is not necessarily what we get year by year by year, but we want to look at this part right here and try to identify a pattern, and based on that pattern write our function. So with this pattern here, we can see that our function over time, so we're going to use f of t. So as time goes by, what does our function do? Well, we take our original amount, $1,000, we multiply it by 1.02, and we're going to multiply 1.02 by however many years we're talking about. So in other words, this is 1,000 times 1.02 to the first, 1,000 times 1.02 to the second in year two, 1,000 times 1.02 to the third in year three, and so on. And so what we're going to do is raise this base 1.02 to however many years that we have. So that's the function that's going to model this exponential growth, or this compounding behavior by 2% annually. So the nice thing about this is we can move on to the second question, and we don't need to build this thing as long as we have our function. So now we want to look at how much money we have after 10 years. So that's simply f of 10 equals 1,000 times 1.02 to the 10th power, and we plug that into our calculator, and we get about $1,218.99 after we round. Alright, so we can use that function to find exactly how much money we have for a particular amount of years. The last question, we want to use our calculator to graph and estimate the amount of time it would take for the money to double. So first thing is we need to make sure that we understand what it means to double. If we start with 1,000, then we need to figure out how much time it takes to get $2,000. So if we set this up, we're looking at 2,000 equals 1,000 times 1.02, and what we're asking is what power. So how many years goes by, or what power do we need on this 1.02 in order to get this answer? So we use our calculator to graph this, and you should get a graph that looks something like this. What we're interested in is, when does this function have a value of 2,000? So we want to go up here to the graph and find where our y value is 2,000. So at this point, right about here, let me zoom in a little bit. This is the point we're interested in. So this point, see if we can get a little more accurate. That's a little bit more accurate. So over here we've got point C. It has a value almost 2,000, and we're looking at just under 35. So if we're using a graph to estimate this, on your graphing calculator you can use either the trace function or you can use a table to come up with an estimate. But essentially, to answer our question, we have this value right here, and that's the number of years. So to answer our question, we go back and we say about 35 years is going to get us $2,000, or in other words, that's how long it takes for our money to double. About. Again, the key here is that we have to estimate this value because we don't have an explicit way to solve for an exponent. Well, that's what we're going to look at, is how can we solve for that exponent, get an explicit answer instead of an estimate. So let's move forward. We're going to move into this slow a little bit. From before, this is the question we just looked at. Again, the key is that we're estimating, and the whole thing here is we're trying to solve for an exponent. We're looking for an exponent, okay? Solving for an exponent. So as we move forward with this concept of logarithms, we'll talk a lot about it, but just keep in mind a logarithm is very simply a way to solve for an exponent. So when we look at logarithms, we're asking what exponent do we have that allows us to complete whatever task we're trying to find. So let's start this process by just asking, kind of in our own terms, what we would need, what exponent would we need to complete the statement accurately. So we take 2 and we raise it to a particular power. We have a particular exponent on 2 and we get 8. Well, we know that 2 to the first is 2, 2 to the second is 4, 2 to the third is going to give us 8. So the exponent on 2 is 3. That's going to give us 8. In other words, 2 to the third power equals 8. Over here, we move on to the second one. 4 to what power equals 64? Well, 4 squared will give us 16. Multiply it by another 4 and we get 64. Therefore, we know that 4 to the third, this is our answer, is going to give us 64. So the exponent there again is 3. This one here is 27 to what power equals 3. Now we're reducing. So anytime you raise a number to a power and you get something that's less, we know we're going to have an exponent less than 1. So let's think about this for a second. 27 to the 1/3 in this case, or the cubed root, is going to be equal to 3, and therefore our exponent is 1/3. So that's our answer. So again, just keep in mind, all we're looking for is an exponent that's needed to complete these statements. So let's get into the technical stuff. So basically what we have here is an exponential function. We know that we raise some base, and we call the base b in general terms. We raise some base to an exponent, and that exponent happens to be y here. And we get some answer x. So some number raised to a power equals x. Well, in logarithmic form, what we say is log base b of x equals or is y. Log base b of x is y. That's how we say this logarithm here, this logarithmic equation. So a couple things that hopefully we can recognize from this is really just 2 ways to write the same thing. So this logarithmic form is just another way to write this exponential function. And notice we have log, and this is a subscript b. This is the base that we're raising to a particular power. So b, it's the same b over here. We're raising that thing to a power, so here's our b. The exponent now, remember we talked about a logarithm. All we're doing is looking for an exponent. Here's your exponent, it's y. And notice in the exponential function, that is your exponent. And in this form, we have the x over here. So when we read this, we should say what power on b, on our base, gives us x. In other words, b to the y power equals x. So these are just 2 different ways of writing the same thing. So we're going to start with that. How can we kind of write this exponential form, or take this exponential form and write it in logarithmic form? All right. So if I want to write this in logarithmic form, I say log base, and the base, remember, is the thing that's being raised to the power, so that's a 5. So log base 5 of this thing over here equals the exponent. So we can rewrite this exponential form as log base 5 of 7 equals x. And that's the same thing, just in a different form as what we had to begin with. Same thing over here. We're going to start and we're going to write this in logarithmic form. So I have log 3 is the thing being raised to the power. X plus 1 goes inside the log. So we have log base 3 of x plus 1. And it's important that we use our parentheses so we understand what's inside the logarithm and what's not. And that's equal to whatever the exponent is. And here the exponent is y. On this last one here, it's kind of flipped around, but we write it in the same general way. We say log whatever's being raised to the power. So that's my base 7 of y in this case, is equal to whatever the exponent is, and that's 2x in this particular case. So here we just have, we're starting in exponential form and we're writing it in logarithmic form. Alright, next thing we want to do, we want to explain in our own words what each one of these things is asking. So log base 12 of x is equal to 2. What this is asking is, what is 12 to the second power? So log base 12 of x equals 2 is just literally asking, what is 12 squared? If we want to write that in exponential form, we would write 12 to the second equals what? Or equals x in this particular case. This is in our own words though. What is 12 squared? That's what this logarithm is asking. In our own words over here, we're going to say what to the third, or what number cubed equals 8. So that's in our own words. So we have x cubed equals 8. Well, we know the answer is 2 because 2 cubed equals 8. But again, we want to look at this, just put it into layman's terms in our own words. What number cubed equals 8? A couple more here. 10 to what power equals 0.01. So 10 to what power? Is 0.01. That's how we put that in our own words. And here we've got what is 11 to the 0 power. Alright, so just kind of converting what we see in the logarithmic form into our own words so we can make sense of it. And we can go through and solve these, and we'll do that on the next page. So here we've got 12 squared equals x, and we know 12 squared is 144. So we've solved that. This is x to the third equals 8, and like I said on that last slide, we know that 2 cubed is going to be equal to 8 because 2 times 2 times 2 is 8. Going down here, this one's a little bit tougher. 10 to what power equals 0.01? Well, 0.01 in fraction form is 1 over 100. So if we start with a larger base and raise it to a particular power and get a smaller number, that means we have to raise it to a particular fraction. And this fraction happens to be -2 because 10 to the -2 equals 1 over 10 squared, which is equal to 1 over 100, or 0.01. So -2 is our answer here, and this is how we can check it. Last one. We're going to rewrite this in exponential form. So I take 11, the base, raise it to the exponent. 11 to the 0 equals x. We know anything to the 0 power is 1, so x equals 1. So just to kind of recap what we've done here, we've taken things from exponential form and written them in logarithmic form. Like these three right here, they started in exponential. We can write them in logarithmic form. These guys here, we started in logarithmic form, we converted them to exponential form, and a lot of times that helps us to kind of wrap our head around what's going on with these particular logarithmic problems. Next thing we want to look at is a particular property of logarithms, and we're going to do that through a little bit of discovery. Hopefully we can identify the pattern here. So this first question asks us what power on 2, so 2 to the what power, is 8. And we've looked at this problem before. We know if we raise 2 to the third power, it's equal to 8. So our answer here, simplifying this, is 3. That's the exponent that we raise the base to in order to get this answer inside the logarithm. Here we've got 2 to the what power equals 8 squared. And we can simplify that because we know 8 squared is 64. So I need to figure out what exponent on 2 gets me 64. So we know 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. And that was 6 2's. So our answer here, the logarithm or the exponent, is 2 to the 6th equals 64. So 6 is my answer here. What exponent on 2 gives me the thing that's inside? So my answer is 6. And I'm just going to rewrite this in a different way. I'm going to write this as 2 times 3, and we'll come back and look at that in a second. This one gets a little bit harder. We can use our calculators here. Again, it's 2 to the what power equals 8 to the 5th. 8 to the 5th is a pretty big number. So 2 to the what power equals, and we can use our calculator to simplify this just for right now, it equals 32,768. So we need to figure out what power on 2 gives us this number, and this will hopefully illustrate my point here. So what we have is, this is going to end up being the 15th power, and you can double check that with your calculator. But again, I'm going to rewrite this in a particular form. I'm going to write this as 5 times 3. So we'll come back to that in a second. Let's do a couple more. 3 to what power equals 9? Well, we know 3 squared equals 9. So our answer here is 2. 3 to what power equals 81? That's going to end up being 3 times 3 times 3 times 3. So 3 to the 4th power. And again, you can double check with your calculator. I'm going to rewrite this as 2 times 2. And then 3 to what power gives us this big number. Hopefully by now, what I want you to do is just stop and see if you can identify a pattern here. Okay? So let's go ahead. I'm going to finish up number 6. We're going to use our calculator. And if you use your calculator, you should come up with 3 to the 8th power. Gives us 9 to the 4th. Or in other words, 4 times 2. So if we take a step back for a second and just look at what we came up with and look at how I rewrote these particular things. Here, pretty simple one, we end up with 3. Here we end up with 2 times 3. So we've got that 3 still in there and we've got that 3 still in there. What I want to highlight though is this number right here. What are we multiplying that exponent by in each one of these to give us the answer? Well, if you look back up at the original problem, and it's the same thing down here. Look back up at the original problem, and basically what we're doing is just multiplying it by the exponent that we're raising what we call the argument, or whatever's inside of the log. So we've got our basic thing here, our basic question, but we can identify this pattern between the exponent and what we're multiplying our ultimate answer from that basic question from. We can come up with a property of logarithms, and essentially that property is we can take this exponent, kind of pull it in front, and then figure out what the answer is to the easy question. In other words, log base 2 of 8 we know is 3, and then just multiply it by the exponent, and that'll give us our answer. So to give you the general rule here, this is affectionately known as the lasso rule, and all we mean by that is we can take this exponent, pull it in front, and then figure out what log base b of x is, and then just multiply it by that exponent. In other words, this simplifies to a times the log base b of x. So this property allows us to find much simpler logarithms and then just multiply it by whatever that exponent is. Why is this useful? Well, we saw why it's useful. We can essentially apply this for these problems, a little bit tougher logarithms, and simplify those things. So this here would be equal to 5 times log base 2 of 8. We know log base 2 of 8 is 3, so this simplifies to 5 times 3. Down here again, these two aren't terrible, but we get to this one, we start to get into some bigger numbers. We can take that exponent, pull it in front, and that simplifies to 4 times log base 3 of 9. We know that log base 3 of 9 is just 2. Multiply that by whatever your exponent was, and we get our answer.